There is a particular kind of quiet that only arrives after the day has completely finished with you. Not silence in the empty sense, not the absence of sound, but the presence of something slower. The kind of quiet where things simply continue without needing your participation. Metal surfaces cooling on their own, dust settling without being asked. The unhurried private business of matter going on being matter, in the dark, with no audience required. That is the quiet you are inside of right now. Whatever you thought about today, whatever was unresolved, unfinished, or still circling in your mind, can stay exactly where it is. Nothing here is required. What happens in this space moves the way warmth moves through a thick stone wall, slowly, layer by layer, from the outside cold toward the inside warmth, and you never notice the precise moment the temperature changes. You only notice that at some point you are warm. Just resting and listening is enough. There is no need to follow any of this closely. Under a low amber lamp, on a plain wooden bench, two objects rest a short distance apart. One glows with the color of old warmth. The other holds the cool, still quality of a winter moon on still water. Neither needs to be touched. Neither is going anywhere. Gold on the left, silver on the right. Two neighbors in the same column of the arrangement of all known things, and yet between them some of the most considered contrasts in all of material science. Contrasts that begin at the surface and travel all the way down to the speed of things too small to see. Tonight we begin exactly there, at the surface, with color. Gold is yellow because of speed, or so current quantum mechanical models describe it. Sit with that for a moment before it goes anywhere further. Not the speed of the metal moving. Gold is famously patient, famously still. The speed being referred to here is the speed of electrons, tiny, invisible, orbiting the nucleus of the gold atom at velocities that approach a meaningful fraction of the speed of light itself. Not metaphorically fast, actually fast, measurably, verifiably fast, in a way that requires the same mathematics used to describe light itself. At those speeds, something subtle happens. The electrons closest to the nucleus pull inward. Their paths curve slightly tighter than they would in a slower, quieter atom. And that small inward lean, that gentle curving of trajectory, changes something that eventually reaches your eye. Gold, because of how its electrons are moving at this deepest level, appears, according to current models, to absorb blue light particularly well. It quietly drinks the cool end of the spectrum in and returns the rest. What comes back to the eye is the warm half, the yellows, the ambers, the soft oranges. The color you associate with candlelight, with old jewelry, with something precious and unhurried. That warmth is not a coating, it is not a coincidence. It is the signature of electrons moving at extraordinary speed, written in light across the face of the metal, readable by any eye that happens to be present. This is what it means to call these metals a molecular mirror. The interior speaks through the surface. What is happening at the deepest, smallest, most invisible level of the atom shows up, directly, quietly, as something the senses can actually receive. You look at gold and, without knowing it, you are reading the behavior of particles moving faster than anything in this room will ever move. The lamp above the bench gives off its own warm amber. It is not bright, barely enough to make the gold glow softly and to give the silver beside it the quality of still water at the end of a long evening. And here nothing is required of you, nor is anything expected. Silver does not do what gold does, and that difference is its own kind of precise. Silver's electrons move at speeds where that inward lean, that curving tighter, does not happen in any pronounced way. There is no particular color being held back. There is no preference, no selection. Silver accepts almost every wavelength of light that arrives at its surface, the warm, the cool, the middle ground, and returns them all, together, evenly, without keeping any of it. Gold, when light arrives, makes a quiet decision. It keeps the blue and gives back the warmth. Silver makes no decision at all. What comes in, goes out, all of it, together, unchanged. This is the source of silver's cool luminosity, not warmth, not preference, but a kind of precise and unhurried even-handedness. It gives light back the way a still lake gives back the sky, completely, without adding anything, without subtracting anything. What you see in polished silver is simply light returned. Measured carefully, polished silver gives back somewhere between 95 and 99% of all the light that reaches it, almost everything, almost all of it returned. Gold gives back somewhat less and unevenly, generously in the warm range, quietly holding on to the blue. The entire visible difference between these two metals, one warm, one cool, one gold, one silver, appears, according to current understanding, to trace back to that single quiet distinction. There's something worth staying with here before moving further. These colors are not aesthetic accidents. They are not choices made at the level of the surface. They are the colors of two different atomic architectures expressed outward in light. The atom speaks, the surface translates, the eye receives. A molecular mirror moving in both directions. There is nothing here that requires your eyes. Everything from here arrives just as clearly in the dark. The details will still find you. They always do in this kind of quiet. Gold becomes strange at extreme thinness, genuinely, quietly strange. Gold can be worked into sheets thinner than a single cell in the human body, thinner than the membrane separating one living thing from everything outside it. At that scale, at a thinness the fingers could not register as anything other than nothing, the warm metal does something it does not do at any ordinary thickness. It becomes partially transparent, and what passes through it is not yellow. It is a pale, cool blue-green. The very color gold ordinarily holds back slips through when the metal runs out of depth to stop it. The warmest of metals, made thin enough, transmits what it ordinarily withholds. This is something material science returns to across different materials in different contexts. The properties of a substance are not fixed points. They are conditions. They shift with scale, with thickness, with how the light arrives, and at what angle, and through how much. Gold at full thickness is warm and opaque. Gold at near nothingness becomes cool and open. The same element, a completely different conversation between its atoms and the light passing through. Silver at that same extreme thinness also opens to light, but evenly across the full breadth of color, because its even-handedness holds even at the edge of near invisibility. Where gold reveals something different about itself at that thinness, silver simply becomes a quieter version of what it always was. It grows thin without growing different. Then there is weight, and weight is where the body becomes the instrument. Gold has a density that surprises almost everyone who encounters it without being warned. When a piece small enough to close a fist around is placed in the palm, it can feel like something considerably larger than it appears. The eye may set an expectation in the mind, and yet what the hand holds can offer a wholly different sensation. There is a brief, quiet recalibration, the mild, pleasant surprise of mass that does not match volume, of something small that insists on being taken seriously. This comes entirely from how gold atoms arrange themselves. They are heavy atoms, and they find each other's company closely, settling together with the patient efficiency of something that has spent a long time discovering its most comfortable configuration. High mass, close arrangement, very little emptiness between them. A density the hand cannot anticipate from the eye alone. Silver is built from the same deep instinct, the same preference for close, orderly arrangement between atoms. But silver atoms are lighter. The result is a density roughly half that of gold. Still meaningfully heavy, still a metal that announces its own presence clearly when lifted. But the difference between holding one and the other is immediate and unambiguous, felt before any number is consulted. Gold anchors, silver settles. The sound of working gold is a muffled, absorbed sound, a thud that the metal swallows almost immediately, the way thick earth absorbs rain, quietly, completely, without echo. The sound of working silver, though somewhat louder and sharper in that initial moment, rings considerably longer, the way a single note holds in a still room before it finally, gently lets go. One absorbs, one releases. The difference is not craft, it is the physics of the inner arrangement, heard from the outside. So the first layer of the molecular mirror has been brought slowly into view. Two metals, neighboring elements, the same deep instinct for how atoms prefer to arrange themselves close to one another, and yet every surface tells a different story, in color, in warmth, in the weight that settles into the hand, in the sound made when touched. Because the surface is not decoration, the surface is translation. It is the signature of arrangements and speeds and behaviors happening at a scale no instrument in this room is built to observe directly. The interior made visible. And yet the eye reads it, the hand reads it, the ear reads it. Every warm glow of gold and every cool return of silver is information, something that arrives directly, quietly, as something the senses can actually receive. The metals rest under the amber lamp, exactly where they are, and you too can be exactly where you are. There is a particular patience to old metal that has nothing to do with the surface, not the color, not the luster, not the warmth a low lamp draws out of gold, or the cool reflection it returns from silver. It is a patience that registers only when time itself is placed alongside the object. Not years, not centuries, but something longer. The kind of time that makes a human lifetime feel like a single breath drawn and released. Matter does not remember, it simply continues. That idea is worth resting with before anything else arrives. The gold and silver under this lamp carry no record of where they have been, no impression of pressure, no trace of heat, no residue of the long geological movement that carried them from wherever they began to wherever they were eventually found. Their atoms are arranged exactly as their structure requires, close, orderly, without urgency, and that arrangement holds no history. Metal refined 1,000 years ago and metal refined last month behave identically under the same conditions, same response to light, same weight in the hand, same quiet indifference to everything that preceded this moment. There is something restful in that. You don't have to hold on to what happened today. Neither does the metal. Neither does anything in the end that is simply made of atoms doing what atoms do. Both metals, the gold under this lamp, the silver beside it, came up through the rock over a long time, not from the surface, not from any visible place, but from within the geological structure beneath. According to current scientific understanding, both were largely absent from Earth's outer layers during the planet's earliest period, the long cooling and settling that produced the crust, the rock, the slow geological architecture that underlies everything standing on it now. Elements as dense as gold moved inward as the young planet found its shape, drawn by the same quiet logic that pulls everything heavy toward the center of things. Most of Earth's gold, under that logic, should be unreachable, locked deep below any surface process, any human hand, any light. What returned these metals to the crust was slow geological work, the patient movement of heated water through rock over immense stretches of time, the way warmth moves through a thick wall in winter, gradually, without announcement, and the long pressure-driven migration of ore upward through the crust. That migration eventually concentrated deposits of both metals into the places human hands would learn to locate and extract. Every gold object ever shaped, every silver surface ever polished, the material in both waited, without anything resembling impatience, for the conditions that would allow it to be found. The bench is still. The lamp gives its quiet amber. Somewhere in the wall behind, in one place, the old building settles a fraction, a sound so low it is felt more than heard, the way a stone accepts the weight of everything above it, without comment, without resistance. There is gold in the ocean right now, or so the available evidence consistently maintains. Not resting on the sea floor, not waiting in any recoverable form, dissolved, dispersed through the full column of water, from the bright shallows to the absolute dark of the deepest trenches, present at a concentration so dilute that any given measure of seawater would yield almost nothing to any ordinary instrument, And yet, when that concentration is multiplied across the full volume of every ocean basin on the planet, current scientific estimates place the total somewhere near 20 million metric tons. 20 million metric tons, dissolved, invisible, moving. It circulates with the great slow currents that carry heat and salt between ocean basins. The water that carries it is cold at depth, heavy with pressure, dim, moving at a pace that has no equivalent in any surface experience. It has passed briefly through the tissues of ocean creatures, incorporated into the chemistry of living things, then released back into solution as those things returned to the water. It is present in the water moving above the deepest, most lightless parts of the ocean floor. It is present in the warm shallows near every shore. In every measure of seawater collected from any point on any ocean at any depth, there is a share of it, real, measurable, and so completely distributed that no technology developed so far has recovered it at any useful scale. The ocean holds it the way the night sky holds starlight, present in every direction, available to nothing, moving through distances that make the idea of collection meaningless. That image, 20 million metric tons dissolved into moving water, drifting through depths where no light has ever reached, spreads before it can be fully held. The mind reaches for it and finds only the open water, which is perhaps exactly the right response. Some things are large enough that resting near their edges is the closest available approach. Silver behaves differently in the ocean, and the difference is, in its way, a kind of quiet adaptation, a slow chemical conversation that gold never enters into and never needs to. When silver is submerged in seawater for extended periods, something begins to happen at its surface, slowly, at a pace no eye could follow in any single observation. The chemistry of the water, which carries dissolved salts that silver is more willing to engage with than gold is, begins to convert the outermost layer of the metal, not dissolving it, not wearing it away, transforming it, building a thin, gray matte surface layer of a silver compound directly onto the metal underneath, one layer of atoms at a time, over months and years and decades of patient accumulation, the way silt settles onto a riverbed, invisible in any single moment, undeniable across years. That converted surface, once established, begins to protect what lies beneath it. The same chemistry that formed it slows further contact with the silver below, a quiet halt, not by design, but through the ordinary logic of atoms finding a more stable arrangement with their surroundings and remaining there. A passive armor assembled from the very process that began as an intrusion. Ancient silver recovered from shipwrecks has been found in exactly this condition. Surfaces gray and matte, nothing like the bright mirror of fresh silver, but cores intact, the original structure preserved beneath the converted surface. The original trace character of the metal, the fingerprint of the ore and the smelting, and the hands that shaped it, all of it continuous and readable, sealed inside that gray outer layer, the way a letter is sealed inside an envelope that the years have weathered without opening. The ocean altered the surface to preserve everything behind it. Centuries of cold, pressure, and slow chemistry, and the silver simply adapted, and held. The interior of a shipwreck in cold water, far below the reach of any surface light. Pressure, the slow movement of current, the faint, low resonance of the ocean above, a weight more than a sound, a presence rather than a noise. The silver in the hold does not experience any of this. It simply reacts, or does not react, according to what the water immediately surrounding each surface atom is offering at that moment. One new layer, then another, decade after decade. A building in the dark that nothing observes and nothing interrupts. And inside it, the metal's original self, unchanged, continuous, exactly as it was the day the ship went down. Gold in that same water tells a different story, or rather, and this is the more precise way to say it, gold tells almost no story at all. Where silver adapts by entering into a careful, limited chemical agreement with its surroundings, gold simply remains. Its atoms have, by every available measure, almost no willingness to engage with any natural environment found at Earth's surface. Seawater does not offer gold anything it is willing to accept. Freshwater does not. Gold recovered from the seafloor retains the same cool, dense weight in the hand as the day it was cast. Nothing in the water has touched it. The mildly acidic chemistry of waterlogged sediment does not engage it. The oxygen-rich air at the surface does not. The water arrives at gold's surface, carries its chemistry close, and nothing opens. No layer forms, no exchange begins. Gold objects recovered from submerged sites have been found in a condition that remains, even when the reason for it is well understood. Surfaces undisturbed, metal intact, indifferent to everything the water attempted. A face worked in relief, an inscription pressed into a coin, the deliberate mark of a craftsman's tool, preserved through centuries of cold and darkness and pressure, not because anything actively protected the surface, but because nothing in the surrounding environment was capable of beginning any kind of conversation with it. This is not resistance in the sense of resisting slowly. Gold does not corrode slowly in natural conditions. According to all available measurement data, it essentially does not corrode. Not a point on a spectrum of resistance. For every natural environment available at this planet's surface, the end of the spectrum, the place where the spectrum stops. Silver, patient enough to endure millennia, reactive enough to build its own protection, rests one quiet step below that absolute position, not as still as gold, but holding in its own particular way, willing enough to engage, stable enough to persist. Gold holds by engaging with nothing. Silver holds by engaging with just enough. Both, in the end, simply hold. And somewhere in that shared outcome is what human cultures across every era recognized in these metals long before the atomic reasons for it were understood. Gold and silver do not change, they remain. You can submerge them, bury them, leave them in darkness for longer than any civilization has existed, and retrieve them as they were. That quality is what made them matter, long before any market assigned them a price. Not reputation, not story, simply how their atoms are arranged and what those atoms are and are not willing to do. The lamp above the bench gives its quiet, unchanging amber. The metals rest where they were placed. The night continues outside, unhurried. The human body carries gold, not as metaphor, not as trace contamination from environmental exposure in any meaningful clinical sense, but as a genuine component of biological chemistry, present in measurable quantities in blood, in joint fluid, in the soft tissue of organs. According to current scientific data, the average adult human body carries approximately 0.2 milligrams of gold distributed across its various compartments. That figure, and it is by any measure a genuinely small one, carries no particular physiological significance at present scientific understanding. No established biological rule for gold has been confirmed in human metabolism, the way rules have been confirmed for iron or zinc or copper. But the gold is there, measurable, real, cycling through the bloodstream in ionic form, incorporated into trace amounts of biological fluid, present in the synovial fluid that lubricates joints in concentrations that researchers have been able to quantify through careful spectrographic analysis. The reason gold ends up in biological tissue at all is rooted in the same geochemistry discussed earlier. Gold is present in soil, in water, in the plant matter that enters the food chain, in the aquatic organisms that filter seawater continuously. The concentrations at each stage are extraordinarily low, but they are not zero, and biological systems that process large volumes of fluid and food over a lifetime accumulate trace quantities of many elements that have no assigned metabolic role. Gold is among them. The body neither seeks it nor particularly expels it with any efficiency. It simply passes through, or lodges briefly in tissue, or circulates in plasma at concentrations that modern analytical chemistry can detect, but that would have been completely invisible to any measurement technology available even a century ago. What this means, practically speaking, is that the gold in a museum display case and the gold distributed invisibly through a living human body are chemically identical in their elemental form. The same atomic number, the same electron configuration, the same face-centered cubic tendency when they aggregate into solid form, each atom settling into the same repeating geometric arrangement, seated in a predictable position relative to its neighbors, the way tiles settle evenly into a floor. The difference between the coin and the biology is simply one of concentration and context. At 0.2 milligrams distributed across roughly 70 kilograms of biological material, gold in the body is present at a ratio of about 3 parts per billion by mass. At that dilution, the atomic behavior of gold is no different than it would be in any other chemical environment. The atoms do not know they are inside a living system. They follow the same electrochemical rules they follow everywhere. There is something in that, the sameness of atomic behavior regardless of context, that has a particular texture to it. Not cold, exactly, more like the feeling of a smooth, flat stone that has been warmed slightly by an afternoon indoors. Neutral, consistent, untroubled by where it happens to be. Silver's relationship with biological systems is considerably more active than gold's, and in ways that have been recognized, studied, and applied across a remarkably long span of human technological history. Silver ions, Silver atoms that have lost one electron and carry a positive charge, designated in chemical notation as Ag+, interact with biological membranes in ways that are measurably disruptive to certain categories of microorganisms. The mechanism, according to current microbiological understanding, involves several overlapping processes. Silver ions bind to proteins in bacterial cell walls, altering the membrane's structure at the surface, the outer boundary of the cell, which the bacterium depends on to hold itself together. Silver also interacts with sulfur-containing amino acids in bacterial enzymes, changing the molecular geometry that those enzymes require to function. And silver ions appear to interfere with the respiratory chain, the sequence of reactions through which bacteria generate usable energy, by binding to components the system cannot easily dislodge. The disruption accumulates from multiple directions at once, something like a lock with several tumblers, each one shifted slightly out of position, quietly, at the same time. The result is that environments where silver ions are present in sufficient concentration tend to be inhospitable to a broad range of bacterial species. This is not a modern discovery. The observation that silver containers kept water and other liquids fresher for longer periods was documented across multiple independent ancient cultures, not because those cultures understood anything about ions or bacterial membranes, but because the empirical pattern was consistent enough to be noticed and acted upon. The molecular explanation came much later. The effect itself was being used practically, in a rough and observational way, for a very long time before anyone knew why it worked. In contemporary materials science and medical research, the silver antimicrobial behavior of silver is studied with considerably more precision. Silver nanoparticles, particles of elemental silver with diameters in the range of 1 to 100 nanometers, have a much higher surface area to volume ratio than bulk silver. The way to hold this, a handful of fine silver powder has more of its material exposed at the edges than a solid bar of the same total weight, more atoms at the surface available to release ions into the surrounding environment, the way a loosely stacked pile of coins presents more metal to the air than a single compressed block. This geometric relationship makes silver nanoparticles considerably more active, ion for ion of silver used, than bulk silver surfaces. The field of research examining their potential applications is large and ongoing, and the data, according to current scientific literature, is still accumulating. The precise dose-response relationships, the long-term environmental behavior of nanoparticles, and the potential for bacterial adaptation to silver ion exposure are all areas where available evidence does not yet provide complete certainty. What is well established is the basic mechanism. Silver ions interact with bacterial biology in multiple simultaneous ways, making it difficult for bacteria to develop resistance through any single mutation. The multi-target nature of silver's antimicrobial action is considered, in current microbiological understanding, one of its distinguishing properties compared to many conventional antibiotics, which tend to operate through more specific molecular pathways. Gold, by contrast, is largely biologically inert at the ionic and nanoparticle level under normal physiological conditions, which is precisely what makes it useful in certain very specific medical applications. Gold nanoparticles are studied extensively as potential delivery vehicles for therapeutic molecules because their surfaces can be chemically functionalized with relative ease. Their size can be controlled during synthesis with high precision, and their core, the gold itself, does not interfere with biological chemistry in the ways that more reactive metals would. The gold is, in those applications, essentially a passive scaffold, present not for what it does chemically, but for what it allows to be done to its surface. The contrast is clean and measurable. Silver acts on biology. Gold allows biology to act on it. Two metals, adjacent on the periodic table, sharing a crystal structure, arriving on Earth through the same geological history, and yet one is a participant in biological chemistry, and the other is very nearly a bystander. Running a fingertip along the cool surface of a silver object, there is a faint, almost imperceptible resistance. Not friction exactly, but the subtle way that metal at room temperature draws a small quantity of warmth from the skin on contact. Silver is, according to thermal measurement data, the metal with the highest thermal conductivity of any metal, higher even than copper, higher than gold, higher than aluminum. Its value for thermal conductivity sits at approximately 429 watts per meter Kelvin at room temperature. What this means in physical terms is that heat moves through silver faster than through almost any other solid material. When skin touches silver, that small exchange of warmth happens quickly, and the perception of coolness is immediate and slightly prolonged compared to touching other metals of the same temperature. The silver is not colder, it is simply faster at conducting the warmth away from the point of contact, maintaining the temperature differential at the skin's surface for just a moment longer than a slower conductor would. Gold's thermal conductivity at approximately 318 watts per meter Kelvin is lower than silver's, substantial by any standard, placing gold well above most materials in thermal performance, but definitively second to silver in this particular comparison. The difference matters in applications where thermal management is the primary design concern, and it is one of the reasons that silver, not gold, tends to be the preferred material in high-performance thermal interface applications in certain engineering contexts, despite gold's other advantages. There is a related property that follows from thermal conductivity and shares its underlying physical origin, electrical conductivity. Silver holds the distinction, according to current materials data, of being the element with the highest electrical conductivity of any metal at room temperature. Its resistivity, the measure of how strongly a material opposes the flow of electrical current, sits, according to current measurement data, at approximately 1.59 times 10 to the negative 8th ohm meters at 20 degrees Celsius. Gold's resistivity, at approximately 2.44 times 10 to the negative 8 ohm meters under the same conditions, is meaningfully higher, about 53% more resistive than silver. In practical terms, silver conducts electricity somewhat more efficiently than gold, atom for atom, volume for volume. And yet, gold is used in electrical contacts, in printed circuit connectors, in the bonding wires of semiconductor packages, far more extensively than its conductivity advantage might suggest. The reason returns consistently to what was established in the previous layer of this examination. Gold does not oxidize. Silver does. A silver electrical contact exposed to air and the trace sulfur compounds present in almost any inhabited environment will develop a surface layer of silver sulfide over time, a compound that is considerably more electrically resistive than the underlying metal. The contact's conductivity degrades. Gold's contact surface does not undergo that transformation. It remains conductive indefinitely in environments where silver would slowly compromise itself. The engineering decision between the two metals is not simply about conductivity. Chemical stability matters alongside it, and the environment a component will inhabit, and the cost of the material. Gold costs more and conducts slightly less, but it stays conductive over time. Silver costs less and conducts more, but its surface changes in air. Neither is simply better. The choice depends on what the application requires. The metals do not compete with each other in any meaningful sense. They simply have different properties, rooted in different atomic architectures, and those properties make them suited to different situations, specific, measurable, particular to what each task requires. The lamp on the bench holds its steady light. The silver surface catches it cleanly, evenly, without editorial preference. The gold surface holds it warm, pulls the yellow frequencies close, and lets the rest go. Deeper still, there are lattice structures to examine, crystal geometries, the specific way these atoms arrange themselves when given enough thermal energy to find their preferred positions and enough time to settle into them. That layer of the comparison waits, patient as the metals themselves, in what comes next. The lamp is still burning. The bench holds the same two objects it has held since the beginning. The gold to one side, the silver beside it, neither one changed. What follows in this video may be useful to you. Perhaps not, but you do not need to watch or listen closely for any of it to find you. The Sleepy Alchemy channel and this video asks nothing of your attention. The material arrives at whatever pace suits the moment, and so the structure of metal is patient enough to arrive in pieces or in passing, or only partly. Every solid metal has an internal architecture, not a visible one, not something that announces itself at the scale of surfaces and edges, but a geometry that exists at the atomic level, repeated with precise regularity across billions of atomic relationships, until the cumulative effect of all that small-scale order produces the large-scale properties that a hand can feel and a tool can work with. The architecture of gold and silver at this foundational level is the same. Both metals crystallize under standard conditions in what materials science designates as a face-centered cubic structure, something like the way identical tiles can be arranged to cover a floor completely, except carried into 3 dimensions, so that each atom occupies a position at the corner or the face center of an imaginary cube, and the pattern propagates without interruption in every direction through the bulk of the material, with 12 nearest neighbors arranged around each atom. 12 nearest neighbors. That number is not incidental. It is the maximum number of equal-sized spheres that can simultaneously touch a central sphere of the same size, a geometric fact proven mathematically long after metallurgists had empirically identified it. The 12-fold coordination means that each atom is surrounded by the maximum possible number of equivalent neighbors, as thoroughly embedded in its local environment as geometry permits. The structure, in the language of crystallography, is close-packed, which means it achieves one of the densest possible arrangements of spheres in three-dimensional space, with approximately 74% of the total volume occupied by atomic material, and the remaining 26% as the interstitial spaces between atoms. Hold a piece of gold, and there is a weight to it that seems disproportionate to its size, a cool, dense heaviness that registers before the eye has fully adjusted to what it is looking at. That weight is a direct consequence of how completely the atoms fill the available space. This geometry has consequences that propagate all the way up to the scale of human hands working metal with tools. Face-centered cubic metals, as a category, tend to be ductile, meaning they can be drawn into wire, and malleable, meaning they can be flattened into sheets without fracturing, even under substantial mechanical deformation. The reason lies in how the planes of atoms within the crystal respond to applied stress. When force is applied to a face-centered cubic metal, the atomic planes can slide past one another along specific crystallographic directions, directions where one plane of atoms can shift relative to the next without breaking the bonds between them. The atoms simply find new neighbors, the lattice shifts, and the metal deforms. And because face-centered cubic crystals have a large number of these available slip systems, something like having many routes through the same terrain, the deformation can proceed through many different geometric pathways before the material runs out of options and begins to crack. The feeling of that, metal yielding rather than breaking, has a particular quality when encountered at the scale of worked material. A thin sheet of gold pressed between smooth surfaces gives gradually, continuously, without drama. There is no sharp threshold, no sudden change in behavior, just a steady, patient accommodation of the applied force, atom by atom, plane by plane, until the sheet is thinner than it was before, and the metal has simply accepted its new geometry. Gold's ductility within the face-centered cubic family is exceptional, even by comparison to other close-packed metals. According to current materials data, a single troy ounce of gold, approximately 31 grams, can, in principle, be drawn into a wire approximately 80 kilometers long. The wire would be real, conducting electricity, reflecting light, maintaining its crystal structure along its entire length, with a diameter measured in micrometers at the threshold of unaided vision. A wire that fine, held between two fingers, would offer almost no resistance. Cool, nearly weightless, with a surface the fingertip cannot fully read. The metal is still entirely itself. It has simply been moved, atom by atom, into a longer arrangement. What makes this possible is not simply that gold atoms are willing to slide past each other. It is also that gold has a relatively low tendency to work harden, a phenomenon in which accumulated defects progressively resist further deformation. Many metals work-harden rapidly. The more they are deformed, the harder and more brittle they become, until eventually they must be annealed before deformation can continue. Gold work-hardens, but more slowly and gently than many of its metallic neighbors. Its lattice accommodates a relatively high density of deformation-induced defects before the material's behavior changes significantly. This is part of why gold has historically been workable with relatively simple tools, cooperating over extended deformation without requiring frequent annealing. Silver's ductility is also remarkable by most metallurgical standards, though it sits somewhat below gold's in this particular comparison. Silver work-hardens more readily than gold. Its lattice accumulates deformation-induced defects at a faster rate, and silversmiths working sheet silver or drawing silver wire have historically needed to anneal their material more frequently than goldsmiths working equivalent gauges. This is not a dramatic difference in practical terms, but it is measurable and real, and it has shaped the craft traditions around these metals in subtle ways, the rhythms of heating and cooling that interrupt the mechanical work, the way the material's changing response under the hammer signals when reheating is needed. The sound of silver being worked changes as it work-hardens. Fresh annealed silver has a slightly duller response to the hammer. The crystal structure is relatively free of defects, and the material deforms with quiet compliance. As deformation accumulates, as the dislocation density within the lattice increases, the metal responds with a fractionally brighter, slightly higher frequency ring, a change subtle enough that it requires experience to read, but consistent enough that it can be read. The material communicates its internal state through sound. The physics of deformation is audible if the conditions are quiet enough and the attention is directed appropriately. There is a coolness to annealed silver that is distinct from the cool of silver at rest. When the metal has been heated to its annealing temperature, somewhere in the range of 600 to 800 degrees Celsius, depending on purity and prior processing, and then allowed to cool slowly in still air, the surface acquires a faint matte quality, a momentary softening of its usual mirror finish. The oxide layer that forms briefly during heating and then partially dissipates as the metal cools, leaves a surface that feels microscopically different under a fingertip than polished silver. Not rough exactly, but with a texture that registers at the threshold of tactile perception. A moment later, polishing restores the mirror quality, but in that intermediate state, the surface carries a record of what the metal has just been through: heat, disorder, recrystallization, slow return to equilibrium. Recrystallization is the process at work during annealing. During plastic deformation, the kind that changes a metal's shape permanently, the internal structure of the crystal is progressively disrupted. Dislocations, line defects in the crystal lattice where the regular atomic arrangement is interrupted, the way a single offset stone in a wall shifts the rows around it, multiply and tangle as the deformation continues. The stored energy in those accumulated defects is real, measurable, and when sufficient thermal energy is supplied by annealing, the atoms become mobile enough to reorganize. New grains begin to form, regions of relatively defect-free crystal with a coherent internal orientation, each one a small area of restored order within the disrupted structure, and grow outward through the deformed metal, the way clarity returns to stirred water once the motion stops, until the entire volume has been replaced by a new generation of grains whose internal lattice is far more regular than what it replaced. The metal, after annealing and slow cooling, feels different under the hammer, not just in temperature, but in response. Where the work-hardened surface had that fractionally higher ring, the annealed metal gives again with the quieter, more compliant sound of restored structure. The craftsperson holding it knows, without measuring anything, that the cycle can begin again. The new grains are not identical to the original grains. They have different sizes, different orientations relative to each other, different boundary geometries. But they share the same face-centered cubic structure, the same atomic spacing, the same fundamental lattice. Recrystallization restores the workability of the metal without altering its elemental identity. The silver is still silver, the gold is still gold. Only the defect structure has changed, wound down, redistributed, replaced by a cleaner arrangement that can accept new deformation before it again reaches the state of mechanical exhaustion that required the annealing in the first place. This cycle, deform, anneal, deform again, is at the heart of most historical metalworking with gold and silver. It is a rhythm of use and recovery, of mechanical input and thermal restoration that craftspeople understood empirically long before any crystallographic framework existed to explain what was happening at the atomic scale. The cycle works because the metal's lattices are structured in a way that allows it. The face-centered cubic geometry is not incidental to the history of gold and silver craftsmanship. It is, in a very direct sense, the physical reason that history exists at all. Without the slip systems of a face-centered cubic lattice, without the ductility and the annealing response those slip systems make possible, gold and silver would not have been the workable, shapeable materials that every metalworking tradition across human history has relied upon. They might still have been beautiful, they might still have been chemically stable, but they could not have been shaped into the forms that made them culturally significant, not by hammers and draw plates and the patient hands of craftspeople working by firelight, anyway. The structure of the crystal, invisible and unreachable at any scale of direct observation available before the 20th century, was nevertheless the enabling condition for everything that was built from these metals across all of recorded time. The lattice made history possible, a fact worth resting beside, without needing to follow it anywhere further tonight. The bench holds its two quiet objects. The lamp holds its amber light. And somewhere in the bulk of each metal, the face-centered cubic arrangement holds itself together with 12-fold coordination and the patient geometry of close packing, exactly as it has, without interruption, since the atoms first cooled into their current positions. There is a layer of gold so thin it cannot be seen as gold. It exists as a coating, a film of metal deposited with precision onto the curved inner surface of a polycarbonate visor, at a thickness measured not in millimeters or even micrometers, but in nanometers, billionths of a meter, closer in scale to the wavelength of visible light than to anything a machining tool could address directly. This film is real, functional, present on every helmet visor used in extravehicular activity. According to current aerospace materials documentation, the gold coating on a spacesuit visor is approximately 100 to 200 nanometers thick, a quantity of gold so small distributed across the visor's surface area that the total mass of the coating is measured in fractions of a gram. And yet, that vanishingly thin layer of metal performs one of the most consequential optical filtering functions in human spaceflight. The reason is infrared radiation. Beyond Earth's atmosphere, in the direct line of solar exposure, the energy arriving from the sun is not filtered by any column of air. It arrives across the full electromagnetic spectrum. Visible light, ultraviolet, and a substantial component of infrared radiation carrying thermal energy at intensities that unprotected materials would absorb and accumulate. The visor must allow the astronaut to see, must transmit enough visible light to make work outside the spacecraft possible, while also managing the infrared component enough to keep thermal conditions behind it workable. Gold at nanometer thicknesses does this. The thin film transmits a controlled fraction of visible light, enough to see by, while reflecting a very high proportion of incoming infrared radiation back into space. Almost nothing gets through. The same selective absorption behavior that gives bulk gold its warm color manifests at these extreme thicknesses as a very efficient infrared mirror. The physics underlying this is continuous with what was established earlier. Gold's relativistic electron behavior, the same mechanism that gives it its color, also shapes its interaction with infrared wavelengths in ways that make it, according to optical materials data, one of the best reflectors of infrared radiation available among coating materials. Its reflectivity in the near-infrared and mid-infrared range reaches 98 to 99% under well-prepared deposition conditions. Almost nothing passes. The thermal energy that would otherwise accumulate behind the visor is redirected into space. The astronaut behind the gold film operates in a thermally managed environment created entirely by the optical properties of a layer of metal thinner than a soap bubble. That a soap bubble and a spacesuit visor share a relevant scale of measurement is not a poetic coincidence. It reflects something genuine about the way optical phenomena operate. Thin films of any material, whether water, air, oil, or gold, interact with light at the scale of light's own wavelength, producing effects entirely absent at larger scales. The iridescent colors of a soap bubble arise from the same family of optical physics, thin film interference, that governs how a gold visor coating controls its transmittance and reflectance. The mechanisms differ in detail, but share a common address in the physics of light meeting matter at its own scale. There is something worth pausing at in that scale. Light arriving at a surface measured in the same units as its own wavelength. Infrared reaching gold, being returned, the surface left exactly as it was. No heat transferred, no atomic arrangement disturbed. The reflection requires nothing of the material it uses. Silver's relationship to optical technology follows a different historical and physical arc, but leads to an equally precise set of applications. The earliest metal mirrors in the archaeological record were polished bronze, a copper-tin alloy sufficient for practical use across several millennia of human history. Silver mirrors came later. Their optical superiority over bronze was immediately apparent to anyone who compared them directly. The reason is the same one encountered earlier. Silver's spectrally flat reflectance across visible wavelengths means that a polished silver surface returns an image with minimal color distortion, a scene returned without the reddish warmth of bronze or the selective absorption of gold. The development of silvered glass mirrors, glass with a chemically deposited silver backing, transformed both decorative craft and scientific instrumentation across the 19th century. Earlier mirror-making traditions, including the Venetian technique, refined from the 16th century onward, had relied on 10-mercury amalgam applied to the glass back, a different process entirely, with lower reflectivity and significant toxicity. The shift to chemically deposited silver came later and was a meaningful one. The silver mirror reaction, a process in which silver ions held in an ammoniacal solution are reduced to metallic silver by an aldehyde, deposits a thin adherent film of silver metal onto glass. Justus von Liebig developed this process in the 1830s. It became the basis for industrial mirror production. A later refinement of the same chemistry, formulated by Bernhard Tollens toward the end of the 19th century, is still used today as a laboratory test for the presence of aldehydes, a demonstration that remains useful because the reaction is clean and visually unambiguous. In telescopy, silver-coated mirrors served as the primary optical element in reflecting telescopes for much of the 19th century. The large speculum metal mirrors of earlier instruments, cast from a copper-tin alloy, were progressively replaced by glass mirrors with silvered surfaces. The reason was reflectivity. Silver returned more of the incoming light to the focal point rather than losing it to absorption. And in astronomical observation, an exercise in collecting as many photons as possible from very faint sources, even a few percentage points of additional reflectivity translates directly into the ability to observe objects that would otherwise fall below the detection threshold. Silver made fainter things visible. The practical limitation was tarnish. Silver sulfide on an unprotected mirror surface scatters and absorbs light rather than reflecting it cleanly. It degrades optical performance over time in any environment containing even trace quantities of sulfur compounds, essentially any inhabited or naturally ventilated space. Large observatory mirrors required periodic resilvering to maintain performance, the old coating chemically stripped, a fresh layer deposited. This was a recurring operational requirement, not a crisis, but it shaped telescope design and observatory practice throughout the era when silver was the standard. Aluminum eventually replaced it, not because aluminum reflects more. Silver remained superior across most of the visible spectrum. But aluminum forms a thin, stable oxide layer the moment it is exposed to air. That layer is transparent and protective, shielding the underlying metal from further oxidation and holding reflectivity at acceptable levels over longer intervals without recoating. The choice was between two different packages of properties, and which mattered more depended on the context. There is a faint metallic coolness to the thought of a large telescope mirror, a parabolic surface ground and polished to wavelength scale precision, coated with a thin film of silver or aluminum, contained within the tube of a telescope pointed at a sky full of things too far away to visit. The mirror does nothing active. It simply presents its surface to whatever arrives and returns what it can. The fidelity of the return depends on the coating's maintenance, the precision of the surface figure, and the thermal stability of the telescope enclosure. All of that preparation, all of that precision in service of passivity. The best mirror is the one that interferes least with the light it handles. Silver's role in early photography adds a chemical dimension to what has otherwise been primarily a physical story. The light sensitivity of silver halides, compounds formed between silver and the halogens chlorine, bromine, and iodine, was observed and documented in the 18th century. It became the chemical foundation of photographic technology throughout the 19th and much of the 20th. Silver halide crystals, when exposed to light, undergo a partial photochemical reaction. What remains is a latent image, minute silver clusters distributed through the crystal in proportion to the light that fell on each region. Chemical development turns that invisible record into something visible. A reducing agent, a chemical that donates electrons, is applied. It acts preferentially. Silver ions in areas that received more light accept electrons more readily, converting to metallic silver faster. The density of metal that forms is proportional to the light that fell there. The image builds itself from that difference. A developed silver photograph, held at an angle to a light source, has a faint, cool sheen to it, the surface of the paper slightly different in texture where the silver sits densest. The entire process, exposure, latency, development, fixing, depends on silver's particular combination of properties, its sensitivity as a halide to photon absorption, its tendency, once partially reduced, to act as a nucleus for further reduction, its stability as a metal once fully reduced against reoxidation. No other element offered quite the same combination. Gold was explored early in photographic history. It proved capable of producing very stable photographic images. Gold-toned photographs from the 19th century are among the most chemically durable that survive. But silver's greater sensitivity and lower cost made it the practical foundation of the medium. What photography did, in a material science sense, was record the spatial distribution of light, make a photon-silver interaction into a permanent, stable, inspectable object. The image exists as a spatial distribution of silver metal, a map of where light fell, written in the density of the metal that responded to it. And the silver in a photograph, like the silver in an ancient shipwreck or a telescope mirror, is still obeying the same atomic rules it has always obeyed. The face-centered cubic lattice, where it exists in the metallic regions of the developed photograph, is identical in structure to the lattice in a silver ingot or a silver wire. The scale is different. The context is different. The chemistry that produced this particular distribution of metal is different. But the metal itself, at the level of its atomic arrangement, is continuous with all other silver, the same element, the same structure, performing whatever role the environment requires. That continuity, the way the same atomic identity persists across every form and application and scale, is one of the quieter things that material science keeps returning to, not as a conclusion, as an observation. The gold in the visor, and the gold in the ring, and the gold dissolved in seawater are the same element in different concentrations and contexts. The silver in the photograph, and the silver in the mirror, and the silver in the ancient coin corroding gently in a museum conservation department are continuous with each other. Matter at this level does not diversify into categories. It simply appears in different arrangements at different concentrations, doing different things, while remaining underneath all of that variation entirely itself. The lamp on the bench settles its light across both metals without preference. They receive it each in their own way. And below this layer, deeper still, there are electrical behaviors, thermal gradients, and the slow drift of atoms through crystal lattices under the pressure of time, all of it waiting in its own unhurried way to be examined. There is a way of thinking about electrical conductivity that removes it entirely from the abstract and places it in the domain of physical movement. When a voltage is applied across a metal, the electrons in the outermost shell of each atom, the ones not tightly bound to any particular nucleus, free to migrate through the lattice, begin to drift. Not rapidly. The drift is extraordinarily slow, measured in millimeters per second or less under typical current densities. What travels quickly is not the electrons themselves, but the disturbance they create, a wave of electromagnetic influence propagating through the electron population at a speed close to the speed of light in that medium, while the individual electrons shuffle along at a pace that could, in principle, be followed on foot. What impedes this drift, what introduces resistance, is the interaction between drifting electrons and the vibrating atoms of the crystal lattice through which they move. At any temperature above absolute zero, lattice atoms oscillate around their equilibrium positions with thermal energy that increases as temperature rises. These oscillations are coupled, propagating through the crystal as waves. In the physics of solid materials, these vibrational waves are treated as discrete packets, quantized units called phonons. The word is borrowed from the Greek for sound, and there is something fitting in that. The lattice is, at any temperature above zero, filled with a kind of silent vibration, each atom nudging its neighbors, the disturbance spreading outward like a slow ripple across still water. When the electrons drifting through this lattice encounter those ripples, their passage is slowed. That slowing is electrical resistance. As temperature increases, atomic oscillation amplitude increases, phonon scattering becomes more frequent, and resistance rises. Conversely, as temperature decreases toward absolute zero, phonon scattering diminishes and resistance falls. For silver, whose resistivity at room temperature sits at approximately 1.59 times 10 to the minus 8th ohm meters, the decrease in resistivity as temperature drops is smooth and continuous. At liquid nitrogen temperature, approximately 77 Kelvin, silver's resistivity has dropped to a small fraction of its room temperature value. At liquid helium temperatures, near 4 Kelvin, it approaches what materials scientists call residual resistivity, the resistance floor set not by photon scattering, which has become negligible, but by the scattering of electrons from static defects, grain boundaries, dislocations, impurity atoms, vacancies in the lattice. The metal, cooled until its atoms have nearly ceased their motion, settles into a deep and nearly frictionless stillness. Gold behaves similarly in broad temperature dependence, resistivity falling as temperature falls, but its room temperature resistivity at approximately 2.44 times 10 to the negative 8th ohm meters is higher than silver's. Very pure gold, carefully annealed, heated and then slowly cooled to reduce its internal defects, to minimize its defect density, can achieve very low residual resistivity at cryogenic temperatures. The lattice, cleaned of most defects and cooled to temperatures where phonons have nearly vanished, offers very little to scatter the remaining electron drift. The metal becomes a conductor of very low resistance, not a superconductor, which is a qualitatively different phenomenon, but a conductor whose resistance has been reduced to the minimum set by irreducible imperfections in any real crystal. The stillness implied by cryogenic temperatures has its own character, not the stillness of absence, but of things slowing toward a limit they never quite reach, atomic vibrations diminishing but never ceasing, resistance dropping but never reaching zero. The approach to absolute zero is asymptotic, a curve that bends ever closer to the axis without crossing it. Neither gold nor silver is a superconductor under ambient pressure conditions at any temperature so far measured. Superconductivity, the phenomenon in which electrical resistance drops discontinuously to exactly zero below a critical temperature, occurs in certain metals and alloys, but the face-centered cubic noble metals are not among them under ordinary conditions. The very properties that make gold and silver reliable conventional conductors, their loosely held electrons, their stable lattice structures, appear, according to current models, to work against a different kind of electron behavior. In certain metals, electrons pair with each other under specific conditions, forming what are called Cooper pairs, and settle into a collective arrangement where resistance vanishes entirely. Gold and silver do not reach that threshold. Their electrons remain individual, mobile, each one moving through the lattice on its own terms. This is not a deficiency in any practical sense. The applications these metals serve do not require superconductivity. They require stability, reliability, resistance to corrosion, and predictable behavior across temperature ranges encountered in real operating environments. A gold contact at the terminal of an instrument cooled to within a few degrees of absolute zero, still conducting reliably in conditions that would degrade a less stable material. What would be lost if they were superconductors is precisely the predictable linearity of their normal conducting behavior, the smooth temperature dependence that makes them useful as reference materials in precision resistance thermometry, and as reliable contact materials in variable temperature environments. Thermal expansion connects the temperature discussion back to the structural and mechanical properties of the previous chapter. All materials change their dimensions with temperature. Atoms vibrating more energetically at higher temperatures occupy, on average, slightly more space, and the cumulative effect across a macroscopic object is a measurable change in length, area, and volume. Gold's coefficient of linear thermal expansion is approximately 14.2 times 10 to the negative sixth per degree Celsius at room temperature. Silver's is somewhat higher, at approximately 18.9 times 10 to the negative sixth per degree Celsius. A 1 meter bar of silver expands roughly 19 micrometers for every degree of temperature increase, less than the width of a human hair. A 1 meter bar of gold expands approximately 14 micrometers over the same interval. In precision engineering applications, optical instruments, microelectronic packages, assemblies where components made of different materials must maintain precise spatial relationships across a temperature range, these numbers matter considerably. When a silver solder joint connects two components, a joint that might be smaller than a grain of rice, sealed within a package no larger than a thumbnail, every temperature cycle imposes mechanical stress on the joint because the two materials on either side are expanding and contracting by different amounts. Over thousands of thermal cycles, this repeated stress can initiate fatigue cracking. The engineering discipline of managing thermal mismatch, selecting compatible materials, designing joint geometries that accommodate differential expansion is a substantial part of electronic packaging work, and silver's thermal expansion value is a fixed parameter every design must account for. Gold's lower thermal expansion coefficient means it changes its dimensions less with each temperature swing, a more stable choice in assemblies that must hold their geometry through repeated heating and cooling. This is part of why gold bonding wire, the fine wire connecting semiconductor chips to package leads in many integrated circuit designs, has been preferred for decades in high reliability applications. In aerospace electronics, in satellites that cycle from sunlight into shadow and back again many thousands of times over their operational lives, the wire must survive the thermal cycling of an entire device lifetime without fatigue failure. And gold's combination of low thermal expansion, high ductility, and resistance to surface oxidation makes it well suited to that requirement. There is a texture to the thought of a gold bonding wire, a strand perhaps 25 micrometers in diameter, looped in a precise arc from a bond pad on a silicon chip to a lead frame contact. The wire is thinner than a human hair. Its loop geometry is calculated to provide enough slack to accommodate differential thermal expansion without placing the wire under tension. The gold is doing what it has always done, being patient, being ductile, being stable, but now at a scale entirely outside the imaginative range of any goldsmith who worked the metal by hand and firelight. Silver's response to extreme mechanical stress includes a behavior known as twinning, which occurs when deformation proceeds faster than the dislocation-based slip mechanism can accommodate. In twinning, a region of the crystal undergoes a cooperative shear. A portion of the lattice reorients itself as a mirror image of its original orientation across a specific crystallographic plane, producing a region whose atomic arrangement is related to the parent crystal by a reflection symmetry. The change is silent. At the scale of a single crystal grain, the reorientation is completed within an interval too brief to observe directly. Twinning is not unique to silver,
but silver exhibits it under conditions of rapid or high strain rate deformation, where other face-centered cubic metals are less likely to engage this alternative deformation pathway. The result of twinning is visible, under the right conditions, even without magnification. When a piece of silver undergoes rapid mechanical deformation, a sharp bend, a sudden impact, the surface sometimes shows faint, straight lines crossing its face. These are the boundaries between twinned and untwinned regions of the crystal, visible because the two regions reflect light at slightly different angles due to their different crystallographic orientations. The metal is recording its own deformation history in a form readable at the surface, a map of where stress was concentrated, where the lattice chose reflection over sliding.
Gold has a higher stacking fault energy than silver, a measure of how strongly the crystal resists misaligning its own layers. Because that resistance is higher, gold tends not to twin under the same conditions that cause silver to do so. It accommodates deformation through a different pathway instead, one where rows of atoms slide past each other gradually, one layer at a time, rather than flipping into a mirror arrangement. This is called dislocation slip, and gold relies on it across a wider range of deformation conditions. The difference is invisible at the surface, but it shapes the faint lines that appear or do not appear when the metal is bent. The bench holds its two quiet objects. Outside, the night continues cooling slowly, the way all things at a slightly elevated temperature eventually cool when left in contact with a larger, cooler environment. The metals on the bench are doing the same, exchanging heat with the air, settling toward the ambient temperature of the room, their atomic vibrations slowing infinitesimally as the night deepens. Deeper in their structure, there is still more to find: the chemistry of surfaces, the slow reactions that time makes visible, and the long electrochemical story that connects these metals to the geological record of this planet. Gold does not tarnish. That statement is short enough to pass quickly, but it contains within it a chemical reality that, when examined at the atomic level, turns out to be one of the more precisely understood phenomena in all of surface science. Tarnish in any metal is the product of a chemical reaction between the metal's surface atoms and molecules in the surrounding environment: oxygen, water vapor, sulfur compounds, and the other gases that constitute ordinary air. For most metals, this reaction proceeds because surface atoms have a thermodynamic tendency to give up electrons, to oxidize, forming compounds whose properties differ substantially from the underlying metal. The examples are familiar. Iron becomes iron oxide, rust, a crumbling, porous material that allows corrosion to continue inward. Copper develops a patina of mixed compounds, basic carbonates and hydroxides, varying with the local atmosphere, commonly called verdigris, the blue-green layer visible on bronze statuary and old copper roofing. Silver becomes silver sulfide, tarnish, a dark gray-brown layer that forms wherever silver is exposed to sulfur-containing compounds in the air. Gold does none of these things under ordinary environmental conditions, and the reason is electrochemical in a precise and measurable way. The tendency of a metal to oxidize is quantified by the standard reduction potential, a number
measured in volts, expressing how strongly a metal ion tends to gain electrons and return to the metallic state relative to a defined reference reaction. Metals with high positive standard reduction potentials are those whose ions most eagerly recombine with electrons, meaning the metallic form is most reluctant to release electrons in the first place. Gold sits at the high end of this scale. Gold's standard reduction potential, how strongly gold resists giving up its electrons, sits at approximately plus 1.5 volts, the highest value among the common structural and decorative metals, and higher than the reduction potential of oxygen in most natural aqueous environments. This means the oxidizing power of dissolved or atmospheric oxygen is insufficient to strip electrons from gold atoms. The thermodynamics do not permit it. A gold ring worn daily for 20 years looks the same as the day it was cast, because at the atomic level, nothing has changed. Gold remains gold, not because of a surface coating or a passivating oxide layer, but because the reaction that would convert it to a compound is energetically unfavorable under conditions found at Earth's surface. This is a fundamentally different kind of stability from what protects aluminum or titanium, for instance. Those metals do oxidize. Their surface atoms react with oxygen, but the oxide that forms is dense, adherent, and electrically insulating, sealing the surface against further oxidation. The protection is kinetic. The reaction happens, but its product blocks further reaction. Gold's protection is thermodynamic. The reaction does not happen in the first place. That distinction matters. Thermodynamic stability is unconditional in a way that kinetic protection is not. Scratch through an aluminum oxide layer, and fresh aluminum immediately reoxidizes. Scratch through a gold surface, and fresh gold is exposed and remains gold, because no available environmental oxidant is strong enough to change it. The luster of old gold has a specific character. A gold surface that has been carried, worn, handled across decades and still presents its original appearance is a record of thermodynamic consistency, proof, visible and tangible, that the atoms at the surface have been offered every oxidizing agent that an ordinary environment can provide across every hour of that time, and have declined each offer without exception. Silver's relationship with its environment is more engaged, more reactive, and more chemically active. The primary tarnishing reaction of silver involves hydrogen sulfide, a sulfur-containing gas present at very low atmospheric concentrations, produced by biological decay, industrial activity, and geological sources. When hydrogen sulfide contacts a silver surface, the sulfur atoms react with silver to form silver sulfide, Ag2S, a compound with a dark brown to black color and a crystal structure entirely different from the face-centered cubic arrangement of the underlying metal. The reaction occurs at concentrations so low that they are imperceptible to human smell. The threshold for tarnish formation is well below the threshold for odor detection. Silver is, in this sense, a more sensitive detector of atmospheric sulfur than the human nose. The kinetics of silver tarnish formation depend on temperature, humidity, and the concentration of sulfur compounds in the environment. Higher temperature accelerates the reaction. The atoms have more thermal energy to overcome kinetic barriers. Higher humidity assists the process because water vapor on the surface facilitates transport of sulfur species to the metal and incorporation of sulfide ions into the growing tarnish layer. The tarnish layer that forms is not perfectly protective in the way that aluminum oxide is. Silver sulfide is somewhat porous and does not completely block continued access of sulfur species to the underlying metal. Tarnishing, once initiated, continues slowly through the tarnish layer, though at a decreasing rate as the layer thickens and diffusion through it becomes progressively slower. If the tarnish layer were thick enough to feel under a fingertip, the growth at its inner face would be imperceptible, atom by atom, slower with each passing day. The electrochemical contact between gold and silver, when the two metals are physically joined or connected through a conducting medium, introduces chemistry that materials conservation specialists must account for. When two metals with different reduction potentials are in electrical contact, even through a thin film of condensed moisture, a current begins to flow between them. One metal, the more willing to release electrons, corrodes preferentially. The other is protected. Electrochemists name these roles the anode and the cathode. In a gold-silver couple, silver has the lower reduction potential. It will tarnish and corrode preferentially adjacent to gold contact points, driven both by direct environmental exposure and by the galvanic couple's electrochemical driving force. This phenomenon is observed in archaeological objects made of alloys or composites of the two metals, with practical implications for conservation. A silver artifact with gold inlay may show preferential corrosion of the silver immediately adjacent to the gold, where galvanic coupling is most effective. The gold is protected, the silver near it is sacrificed. Under magnification, the corroded zone adjacent to a gold inlay presents a pale, rough surface, a change in texture and color visible at the metal's edge. The electrochemistry is indifferent to the aesthetic value of the object. It follows the potential gradient steadily at whatever rate the available electrolyte and temperature permit. There is a gray-brown quietness to tarnished silver that is entirely different from the visual character of the metal when polished. The tarnish layer scatters light in all directions rather than returning it as a clean reflection. It has no mirror quality, no crisp return of an image. What it has instead is a kind of soft, absorptive depth, a surface that takes light in rather than sending it back. The texture under a fingertip is subtly different, faintly rougher at the microscopic scale, the silver sulfide crystals presenting a topography that the underlying face-centered cubic lattice does not. There is history in it, not metaphorical history, literal chemical history, a record of every hour of atmospheric exposure, every fluctuation in ambient humidity, every trace of sulfur compound that found conditions favorable for reaction. The long-term fate of silver in archaeological contexts depends enormously on the chemistry of the burial or deposition environment. In dry, low-oxygen environments, desert conditions, sealed tombs, silver can survive for millennia with only superficial tarnishing because the reactants for continued sulfidation are not present in sufficient quantity or mobility. The silver reaches a kind of chemical stasis, not because the thermodynamics have changed, but because the kinetic pathway has been closed by the absence of mobile reactants. The tarnish layer already present seals the surface modestly. The dry environment removes the humidity, facilitating ion transport, and the reaction rate drops until change across human timescales becomes negligible. In wet, sulfur-rich environments, waterlogged sediments near organic material, soils with active biological communities, silver corrodes more aggressively, with deep corrosion penetrating well into the metal's cross-section. The silver sulfide front advances inward over centuries, sometimes converting the object to a pseudomorph, a form retaining the external shape of the original, but consisting, in bulk, entirely of corrosion product. The shape survives, the metal does not. Gold objects from the same burial environments are typically unaltered. A gold object recovered from a 2,000-year burial site can be lifted from the excavation and reflect light with the same quality it held the day it was placed there. The same soil chemistry, the same moisture, the same biological activity, and gold, surrounded by all of it, remains electrochemically indifferent. Side by side, a gold object and a silver object narrate completely different chemical histories, despite sharing the same physical environment for the same duration. The difference is entirely in their atomic structures, in the electron configurations that determine where each metal sits on the electrochemical series, and therefore how each responds to the same environmental chemistry. That parallel, same environment, different outcomes, both entirely explicable by atomic level properties, is one of the things that makes comparative materials science capable of sustaining long, quiet attention. The explanation is complete. There are no gaps that require inference to fill. The electrochemical series was established experimentally long before anyone understood why it had the values it did. Numbers read from instruments in 19th century laboratories, recorded in notebooks, confirmed across many repetitions, and the quantum mechanical understanding of why gold's reduction potential is so high, which traces back to the way gold's electrons, accelerated by its large nucleus, move fast enough that their mass increases measurably, contract inward, and bind more tightly, came later and confirmed what the measurements had already shown. Measurement first, understanding second. The order of discovery does not alter the completeness of the explanation now available. The bench holds its objects. The tarnish on the silver surface, if there were any, would be doing its quiet work, one molecular layer at a time, at a rate set by the temperature and humidity of the room, indifferent to observation. The gold surface reflects the lamp's light with the same selective warmth it has always reflected it. And beneath both surfaces, the atomic arrangements that determine all of this behavior continue their thermal oscillations, slower now as the night deepens and the room cools slightly, but continuous as they have been, without interruption, since these atoms first settled into their current positions. There is a temperature at which atomic motion becomes, by any practical measure, as close to stillness as matter is observed to reach. It is not absolute zero. That point remains, according to thermodynamic law, permanently inaccessible, a limit that recedes as cooling approaches it, the way a horizon recedes as a ship sails toward it, a boundary that physics permits matter to approach indefinitely, but never reach. The closest that laboratory conditions have brought bulk matter is within billionths of a degree of absolute zero, and even there, the atoms are not still. They retain what quantum mechanics designates as zero-point energy, a residual motion not thermal in origin, arising from the fundamental uncertainty in the position and momentum of any particle confined in space, and which cannot be removed by any cooling process. It must move. Even at the coldest temperature physically achievable, the atoms in a gold or silver crystal are vibrating slightly, inevitably, because their confinement within the lattice requires it. It is not a paradox requiring resolution. It is simply a fact about the nature of matter. The motion is real. It is small. It does not accumulate into anything observable at the human scale, but it is there, at every temperature, without cessation. The lattice vibrates at the quantum floor. And the materials science that describes this, the dB model of lattice heat capacity, the Einstein model of independent oscillators, and more refined treatments, all built on the recognition that atoms in a solid are never simply resting, always doing something, even when that something is the minimum that physics permits. At room temperature, the situation is considerably active. The thermal energy available at 293 Kelvin drives atomic oscillations, small in absolute terms, but large relative to the zero-point motion. In gold, the atoms oscillate around their equilibrium positions with amplitudes on the order of 1/10 of an angstrom, a fraction of the interatomic spacing, but not a negligible fraction. 1/10 of an angstrom is approximately the size of a hydrogen atom, and gold atoms are shifting by that distance continuously at ordinary room temperature in every piece of gold resting on every surface in the world. The oscillations are coupled, propagating through the lattice as phonons, packets of vibrational energy that pass through the crystal the way a slow ripple crosses a still pond, carrying motion from one atom to the next without any single atom traveling far from where it rests, with a spectrum of frequencies determined by the lattice geometry and the interatomic force constants. The highest frequencies in gold's phonon spectrum correspond to oscillations at rates of several terahertz, while the lowest frequency modes involve cooperative motion of large regions at rates orders of magnitude lower. All of these modes are simultaneously active at room temperature, layered continuously through the entire crystal. Silver's phonon spectrum differs from gold's in ways that reflect differences in atomic mass and interatomic bonding. Silver atoms are lighter than gold atoms, approximately 108 atomic mass units compared to gold's 197, and lighter atoms connected by bonds of comparable stiffness oscillate at higher frequencies. Silver's dB temperature, a value that marks the point at which a metal's vibrational behavior becomes fully thermally active, the way a tuning fork's full range of resonance is only heard once it has been struck with enough force, is approximately 215 Kelvin, compared to gold's approximately 170 Kelvin. The higher dB temperature of silver means that a larger fraction of its phonon modes are fully thermally excited at room temperature. The lattice is more completely activated at ordinary temperatures than gold's. This contributes to differences in heat capacity, thermal conductivity, and electrical resistivity at sub-ambient temperatures, reflecting the difference in atomic mass that traces directly to the nuclear physics of these two elements. The sound of a crystal vibrating at terahertz frequencies is not a sound in any sense that reaches the ear. It is motion at a scale and rate entirely outside the range of human auditory perception. The only sounds these metals make at the human scale, the ring of a silver bell, the muffled resonance of a struck gold ingot, are the macroscopic mechanical resonances of the entire object, standing waves involving the coordinated motion of trillions of atoms, whose individual thermal vibrations average out into the elastic medium supporting those large-scale acoustic modes. The object rings, the atoms vibrate. The two phenomena are connected by physics, but separated by many orders of magnitude in scale, each existing in its own register, following its own rules. The geological persistence of gold and silver, their continuity in the Earth's crust across spans of time that dwarf any human framework for duration, is rooted in exactly the chemistry and physics that the preceding chapters have established. Gold's electrochemical nobility means it survives geological processes that chemically transform other metals. Hydrothermal fluids circulating through rock at elevated temperatures dissolve gold from one location and redeposit it in another, not because gold enters permanent chemical combination with the fluid, but because at elevated temperatures and pressures, certain ligands can form soluble gold complexes. When those fluids cool and depressurize, the conditions that stabilize the gold complex no longer hold, and the gold precipitates, returns to metallic form in veins and disseminated deposits at concentrations that geological time and repeated hydrothermal events can build to recoverable levels. The gold in those veins has traveled through the crust, dissolved, transported, redeposited, perhaps incorporated into rock, eroded, washed into river sediment, concentrated by the density sorting action of flowing water into alluvial placers. The weight of a gold flake in river sediment, the way it settles faster than any surrounding mineral, pressing into the gravel under its own density, is the direct physical expression of the same nuclear structure that gives gold its color and its resistance to chemical change. The atom dissolved and redeposited through successive hydrothermal cycles is the same atom a river eventually carried to a gravel bar. The journey was long. The atom was unchanged. Silver's geological history is more chemically eventful. Silver forms compounds, sulfides, chlorides, carbonates, and those compounds are themselves minerals, constituting a significant fraction of the world's silver ore deposits. Silver travels through hydrothermal fluids as sulfide complexes, precipitating as silver sulfide minerals alongside the sulfides of lead, zinc, and copper that characterize many major silver mining districts. The association of silver with lead ores shaped silver production across antiquity. Silver was recovered as a byproduct of lead smelting through cupellation, a process exploiting their different oxidation behaviors. Cupellation is, in material science terms, a precise application of differential thermodynamics. Lead oxidizes readily at furnace temperatures. Lead oxide forms at the surface and is absorbed by the porous bone ash cupel on which the metal rests. Silver does not oxidize under those conditions. Its reduction potential, while lower than gold's, is still high enough that atmospheric oxygen cannot sustain the silver oxide reaction. The lead is progressively removed as oxide, absorbed into the cupel, and what remains is a bead of silver, purified by the selective removal of everything that would oxidize, leaving behind what would not.
There is a slowness to the image of a cupellation furnace cooling after the process is complete. The silver bead on the bone ash surface, bright and still. The furnace temperature dropping degree by degree. The bead solidifying from the outside inward as temperature falls below silver's melting point of 961 degrees Celsius. The solidification front advances through the liquid metal. Grains nucleate and grow, boundaries forming between adjacent grains of different orientation, the microstructure establishing itself in the seconds and minutes of cooling. Both metals carry histories, not in any metaphorical sense, but in a literal, physically readable one. The grain structure records solidification. The dislocation density records deformation. The tarnish layer records atmospheric exposure. The trace impurity distribution records the ore source and smelting conditions. Every object made from these metals is simultaneously an object and an archive, a document of every significant thermal, mechanical, and chemical event since the metal first solidified from the melt. The archive does not announce itself. It requires specific techniques to read: metallography, mass spectrometry, X-ray diffraction, electron microscopy. But it is there, continuous and complete, in every gold ring and silver spoon and coin and wire and thin film deposited onto a visor for use in a vacuum beyond the atmosphere. If one of these details stays with you, it may be worth leaving in the comments. The quietest observations often turn out to be the most interesting ones. The history is encoded in the structure. The structure persists because the chemistry of these metals, rooted in their atomic architecture, allows it to persist. And the atomic architecture was established when the atoms first settled into their face-centered cubic positions in the earliest formations of the crust, and has remained in that arrangement in one object or another continuously since. The lamp on the bench holds its light. The two metals receive whatever arrives and do with it what their electron configurations have always required. Gold returning the warm frequencies, silver returning everything with equal neutrality. Neither is performing. Neither is doing anything other than being exactly what its atomic structure specifies it must be under these conditions, at this temperature, in this light. Outside, the night continues in its ordinary thermal gradient, the Earth's surface radiating accumulated heat, the air above cooling at its own measured rate, the temperature settling toward whatever the season and latitude determine before dawn reverses the process. The gold and silver on the bench are part of that thermal system, exchanging heat with the air at rates determined by their surface areas and thermal properties, settling toward the same equilibrium as everything else in the room. Atoms vibrating at the rate that temperature requires, electrons drifting through the lattice at the rate that the ambient electromagnetic environment sets. Crystal structures maintaining their geometry with the fidelity of close packing and 12-fold coordination, as they have without interruption since the atoms first assumed these positions. Tonight we compared gold and silver, and nothing in this journey was required, nor is anything required now. The examination is complete, not because everything knowable about gold and silver has been said, but because the arc from surface to atom, from color to crystal structure, from geological history to quantum mechanical ground state, has been traversed at the pace that patience permits. The information arrived at its own rate. The metals remained what they are throughout. The quiet of a laboratory after hours is the same quiet it was at the beginning. It does not need anything added to it. It simply continues, as matter does, as these metals do, patient, structured, and entirely at rest within the motion that their nature requires of them. We have now reached the end of the video. If you are still awake, liking the video and subscribing to the channel would help us reach more people who need this kind of content. Only if you feel like it, of course. Good night. Take care of yourself. Until the next video.